Alex.
Thank you, Constantine. Good morning. So I should start by saying that this is joint work with Faivel Fogel, Rodolphe Genaton, and Francis Bach, who are also in Paris. And I just want to do one short advertisement. I'm recruiting several postdocs for 1 or 2 years at École Normale Supérieure. This is the view from our office, more or less. And so if you're interested, and it's over a couple of years, so if you're interested or you think you're going to be interested, please send me an email. I'm very interested. So convex relaxations for permutation problems is a bit vague. And today I'm only really going to focus on 2 problems. And the first of them is seriation. And seriation is very easy to describe. You have a matrix storing similarity information. So Aij is the similarity between variables I and j, okay? And you make one key assumption here, which is that the data has a serial structure, okay? Meaning that, well, roughly speaking, there is a permutation of these variables such that the similarity matrix is decreasing starting from the diagonal. So there is this explicit condition. We're going to say that A pi I pi j is an R matrix after Robinson if A pi I pi j decreases with I minus j, okay? So roughly speaking, this looks like this. And the seriation problem is very easy to describe. You don't get this. What you observe is this, okay? It's a random permutation of this serial similarity matrix, and you need to reconstruct this. Okay? That's it. So that's the first problem I'm going to focus on. The second is the continuous one problem. So seriation is easy to understand, but in fact, it turns out that this is the important one. And they're directly connected. Okay, and in C1P, so this is abbreviated C1P, you're given a 0-1 binary rectangular matrix. And you want to reorder its rows or columns such that the ones in each row are contiguous, okay? So here the problem looks very much the same. You're given this matrix here, and you want to find a permutation of the columns such that what you get is something that looks like this, okay? And here this is a C1P matrix because all the rows have contiguous ones, right? And the connection with seriation is very direct. If you compute C transpose C, the overlap matrix, what you get is an R matrix, okay? So this satisfies the condition I just mentioned. This has a serial structure. Okay, so you have this result from Kendall in '69, which connects the 2 problems, okay? Any questions so far? So why is this important? Well, in shotgun gene sequencing, for example, what you really want to solve during assembly is a C1P problem. So how does the shotgun gene sequencing work? Well, we don't know how to sequence long sequences of genes. So what happens is that they're cut into small pieces, about 400 base pairs. That number increases slowly over time, but roughly speaking, that's the order of magnitude. And the genomes are cloned multiple times, so we get many pieces from many different cloned genomes. And the point is then to reorder this bunch of small reads, they're called reads, so that, well, you can reconstruct a consensus sequence from the small bits, the reordered small reads, okay? So that's shotgun gene sequencing. And why is it connected to the problems I just mentioned? Well, it turns out that reordering these small reads is solving, roughly speaking, a C1P problem. There's a little bit of noise, etc. But essentially, when you have the reads, the small reads, reconstructing the full sequence turns out to be equivalent to solving a C1P problem. Why? Well, if you get the sequences in the correct order and you assume that the length of the reads doesn't vary too much, and you basically identify in the reads small subsequences called k-mers and plot everything in terms of these k-mer positions, if you get the correct order, then the columns of the reordered k-mer versus read matrix will have the continuous one property, okay? So basically, reordering the reads from a shotgun gene sequencing data set amounts to solving a C1P problem, okay? So it turns out, and this is one of those rare miracles where, at least in the noiseless case, we have an explicit solution, that there is a spectral solution to this problem. And curiously enough, it's not being used in gene assembly, and I'm not sure why, but that, maybe we haven't discovered that it doesn't work numerically, but so far our experiments are very conclusive. And so it's very easy to describe. It's based on spectral clustering. So what you do is that you solve this problem that's essentially computing the second smallest eigenvalue of the Laplacian of the matrix A, okay? And it turns out that if you compute the corresponding eigenvector, well, the order of the variables in this vector also gives you the correct reordering that makes A an R matrix, okay? So you're given A up to a random permutation, you compute its Fiedler vector, so the vector you use in spectral clustering, for example. You look at the order in the variables, you reorder them, and then you use the same order to reorder the matrix, and voila, it's in R format. So it has this nice serial structure. And it solves, in particular, the C1P problem, if you look at the squared matrix, okay? And so this result, the one I'm citing here, is due to these authors. But I'm pretty sure, and I'm very interested if you have references in mind, I'm pretty sure this is something that has been rediscovered in different forms in different fields. Okay, so it's probably known somewhere else. You may have your favorite reference, but at least this one comes from one of the SIAM journals, and it dates back from 98. Okay? So I could stop here, but I'm not going to do that. And the reason why I'm not going to do that is that, well, the spectral solution is nice. It's very easy to get a second eigenvector. It's something you can solve at web scales. PageRank roughly does the same thing. So that's really satisfying, but it's only in the noiseless case. And there's a small region controlled by the size of the spectral gap where the spectral solution is stable, so you're fine. But then the question is, what if your data is really noisy? What happens beyond the perturbative regime for the second eigenvector? Okay? So that's one question. What if the noise is high? Suddenly the spectral solution stops working and it's not clear what you get, okay? And how to control the quality of the solution that's left. That's one point, noise. The second is, what happens if you have additional structural information? So I don't know anything about gene sequencing, but clearly the process is a little bit more complex than what I just described. And in particular, you have side information. So you know that, for example, certain pairs of genes should be kept close together, etc. So people know where certain genes should be, so that you have a lot more information than just the similarity between pairs of reads. And the question is, how do you incorporate that information in the spectral solution? It's not clear at all how to do that, and this information is key to resolve uncertainties in the way things should be reordered, because, for example, in gene sequences, there are lots of repeats and so on, which really mess up the process. So there's structured noise in gene assembly. Yes? There are degeneracy issues that can be handled, so you have multiple solutions, etc. But the paper I'm citing has really worked out all the details of what happens in those cases too. They're rare, but they do happen if your matrix is more structured than natural similarity data. So that's well understood too. And there are ways of storing the data efficiently. So that part of the problem is kind of nicely closed. Okay? I mean, unless you have more imagination. So the question here is, we have a solution, we have the spectral solution, but we don't know, in fact, the problem we're solving. So we don't have, in particular, an objective to tell us this solution is better than this one, or something like that. Or we get a solution out of the spectral. We want to do a little bit more greedy optimization. We don't know what to optimize. So we need to reformulate seriation as an optimization problem. Okay? And so seriation, to get an idea of what to do, it's easy to think in 1D. And in 1D, it's very easy to formulate an optimization problem which will serialize the data. So, okay, so you know this very basic result. If you have an increasing sequence A1, AN, okay, if you solve this minimization problem over all permutations, so the scalar product between AI and a permuted version of B, well, there is a trivial solution. You just set pi such that B pi is decreasing, okay? So the original sequence goes like this, and the one that minimizes basically moves in the opposite way. And so that's 1D. So solving seriation in 1D is easy. You just minimize something an objective that looks like this. In 2D, it's a little bit more complex, but the idea is roughly the same. You can write a problem that is suspiciously close to what you're trying to do, called the two-sum problem. And it's mentioned in the Atkins paper, but they don't really make the connection. In two-sum, you minimize this quantity here over all permutations of rows and columns of the matrix A. And basically what you do is that you have this quadratic penalty on the distance to the diagonal, okay? So you heavily penalize terms that are way outside of the diagonal, and you don't penalize so much terms that are close to the diagonal, which is what you want to do, right? And you minimize that over permutations. And so typically this will tend to put the large similarity terms close to the diagonal and the small ones outside. So it seems to do what we want. And the key question is, this is nice because it can be written in terms of the Laplacian of the matrix A. We've seen a lot of Laplacians yesterday. So that's all good news. We sort of suspect this is going to be what we want to solve. Of course, the annoying news is that this is an NP-complete problem, which is different from the 1D scenario. But the question is this really solving seriation? And the answer is, for certain matrices A, yes, okay? And so the way to look at it, to see that, a very brief proof sketch, is just to decompose the matrix A. So you have this similarity matrix, and it turns out that a very nice way for computing a decomposition of the matrix A is to decompose it in terms of cut matrices. And the definition comes from a paper by Fries and Cannon on matrix approximations. And cut matrices are simply squared constant, constant block, symmetric block matrices, okay, 0, 1. It's an elementary block, and we're going to try to write our matrix A, our objective matrix A, as a combination of cut matrices, okay? And why are cut matrices a good choice here? Well, it turns out that the objective can be written in terms of the Laplacian. So this is our two-sum objective. It can be written in this format. And if the matrix A is a cut matrix, then basically what you're computing here is a variance, okay? And so you're trying to find a permutation of the vector y that minimizes the variance if you assign uniform probability weights to all the coefficients, okay? And why is that exactly what you want? Well, if you look at solutions with minimum variance, so here I'm minimizing the objective for a cut matrix with a constant block between variables 5 and 8. Okay, so it's this block here. Minimum variance solutions tend to have contiguous points inside. So all the indices are contiguous here. Okay? So in fact, in particular, this means that the variables are correctly reordered. They're in sequence. Okay? And this is what you want. So as soon as the variables are not in sequence, so there's a gap here, the variance increases. So at least we know by this sort of hand-waving argument that on cut matrices, the two-sum problem actually solves the seriation problem. We serialize the variables inside the block corresponding to the cut matrix, okay? Very roughly speaking. And then the idea is, well, so you have these two results. If you start from a pre-R matrix, you can show that any R matrix or pre-R matrix, which is a permutation of an R matrix, can be written as a combination of cut matrices, okay? So you have the decomposition you want, and you can completely formalize the result I just displayed, which is that the solution of a two-sum minimization over cut matrices has contiguous, consecutive indices, okay? So it does what you want, it serializes the data. And turns out that if you decompose, if your matrix can be decomposed in terms of cut matrices, then, well, you're done, because you know that the solution where all the variables are correctly reordered inside the block is optimal for each particular minimization subproblem corresponding to each cut component. And your objective is just a sum of components. And for each of these components, the consecutive solution, the one where the variables are in the correct order, is optimal. So you're optimal for each little subpiece. So you have to be globally optimum. And that's it. Okay? So basically what you can show is that when the matrix is pre-R, if you compute its square, then the two-sum and the seriation problems, so the two-sum problem will solve the seriation problem on the squared matrix A. So the only requirement here, I'm focusing on R matrices, but the only requirement here is that your matrix has to be written as a combination of cut matrices. Okay? So at least now we have one combinatorial problem which actually solves the seriation problem. And so why do we care? Why is this important? Well, first, there's a nice side effect, which is that we now have a polynomial time spectral solution to the two-sum problem for certain types of matrices A. Okay? So that's nice. The original paper by Atkins and others mentions both problems, but they don't really show the connection, make the connection explicit. But more importantly here, in practice at least, we can now write seriation as a combinatorial optimization problem. And the idea is then to write a convex relaxation for two-sum and seriation. Why? Well, the spectral solution scales very well, but we know it's not very robust. It starts to fail outside of the spectral perturbative regime where the noise is smaller than the spectral gap. And it's not flexible. So the idea here is that we have additional structural information about the solution. We want to include this information in the optimization problem we're solving, and then hopefully relax that problem, solve it, and get a solution that is more robust. Okay? And that's very easy to do. You can write Dn, the set of doubly stochastic matrices. So these are matrices whose rows and columns sum to 1, and which have non-negative components. And this turns out to be the convex hull of the set of permutation matrices, which is the set we really care about. You can also notice that the set of permutation matrices is the intersection of the set, is the set of matrices that are both doubly stochastic and orthogonal. And so we're going to solve a very large quadratic program that looks like this, okay? And I'm not going to let you look very long at this slide and try to infer what's going on. I'll try to explain piece by piece what's going on. So, of course, the constraints here, so our main variable is this matrix capital pi. If all goes well, and that never happens, pi is a permutation matrix, so it encodes the permutation, okay? So it's just a permutation of the identity. And then, well, you have this objective here and the main constraints, and I'll say a few words about these. So the objective looks like this. And this is only a sort of more compact notation for this. And what we do here is that we know we can solve the two-sum problem, solves the seriation problem when yi is equal to I. Okay? And we sort of suspect, and we haven't shown it yet, but it's kind of a source of natural, that if you perturb a little bit the sequence yi equals I, our result, our equivalence between two-sum and seriation still holds, and you get a slightly different relaxation. And it turns out that at least numerically, it's a good idea to average the objective over several choices of these monotonic sequences, index sequences. So we start by sampling points yi, where yi is equal to I, plus a small noise epsilon. And we average the objectives. Okay, so it's a bit of a hack, but it tends to improve things a bit. And so that's nice. And then there's an additional trick, which is to say, well, Our objective is convex. We minimize it so we get a point somewhere in the center of the set of doubly stochastic matrices. The nice permutation matrices we care about are on the edge. So we want to push our matrix, make our objective as concave as possible. And it turns out that we can add at least a small concave component to it, which improves things a bit. It's another hack, but it seems to work. And that's just, it's a very natural penalty because basically among all doubly stochastic matrices, the rotations, hence the permutation matrices, have the highest Frobenius norm. So we're just trying to maximize the Frobenius norm, but we need to maintain the convexity of the objective. And there is an explicit bound on mu that basically keeps the objective convex. And it's simply based on the eigenvalues of y and the Laplacian. Okay? So that's the objective. We're just solving two sum, but for a different set of objectives. And we have this extra penalty to try and concavify the objective. That's it. And one important thing, so what about the constraints now? For the constraints, well, there's just the fact that pi is doubly stochastic plus one extra hack. And this is really extremely important. And it's easy to forget. So if you think about the seriation problem, you actually have always two solutions, two monotonic solutions who solve the problem to optimality in the noiseless case at least. One where the sequence is monotonically, is increasing. And a second one where the sequence is decreasing, okay? And they're both equally good. And it's not an issue if you're trying to compute the spectral solution and so on. It's just a matter of signs. Okay, but as soon as you write a convex relaxation for the problem, when you have these degeneracies, you're in trouble. Because every time you have multiple solutions in a convex relaxation, all the solutions in the middle should be good too. The ones you really care about are the extreme points, but the ones you get are the points in the middle. So if you have degeneracy in a convex relaxation, you should immediately remove it to improve the quality of the relaxation. This is easy to forget, and it makes a huge difference numerically, okay? So the last constraint is simply here to say that among all the possible degenerate solutions of the seriation problem, the one we care about is the one that is monotonically increasing, okay? I'll practice on that. Anyway, so this is a key constraint. It makes a huge numerical difference, but it's just there to lift the degeneracy, okay? So this relaxation is, at this point, simply a hack. We don't have approximation bounds, but it's kind of easy to go further than this. It's not very tight, right? You would just relax permutation matrices as doubly stochastic matrices. The problem is a large QP. Numerically, there is some hope because it has a nice structure, so it's not so bad, but we can do a lot better than that. So I've just said that permutation matrices are matrices that are both doubly stochastic and orthogonal. And so we can add the constraint that the matrix we're looking for is orthogonal and try to relax it. And that turns out to be a somewhat classical problem. It shows up in the Procrustes formulation where you're trying to do alignment. You're trying to align images, for example, or in cryo-EM reconstruction, you have a lot of these alignment problems. So there's a long list of results on how to relax those quadratic constraints, okay? Those orthogonality constraints, sorry. And they're based on a very simple observation, which is that when you have a constraint like this, Q transpose Q is equal to the identity, well, it's an orthogonality constraint, but it's also, if you look at the matrix Q as a vector, it's also a quadratic constraint on the vector Q, okay? And so, well, if you have a non-convex quadratic constraint on Q, you can simply lift it using the traditional semi-definite relaxation technique, okay? And the good news is that in some cases, like Procrustes and so on, you can show very, very tight, almost nearly dimension-independent approximation ratios for these relaxations. So square root of log n. Square root of log n is more or less 6, okay? So the approximation ratios are really good. Unfortunately, from a numerical point of view, this is a complete disaster. Because think about it. The matrix has roughly n square variables in it. You're going to consider that it's a vector, lift it as an SDP. So what you get is an SDP of dimension n square. And if you try to solve that using an interior point method, for example, the complexity you get is n to the power 9. Okay? So that's not exactly a tower of exponentials, but for practical purposes, it's a bit tricky. Okay? It doesn't work beyond dimension 10 or so. So these relaxations are very nice for getting bounds, but in practice and in all the examples, first we've tried them, and they don't seem to make a huge difference in the problem we've considered. And also from a practical point of view, they're completely out of reach numerically. But it's much easier once you have an SDP, et cetera, to quantify the approximation quality, and we don't have anything yet if you use the doubly stochastic constraint alone. Okay? So I apologize for the lack of approximation bounds, but if necessary, we can prove them, but numerically, it's going to cost you. Okay? But so more importantly, in practice here, we can add constraints, and at no cost numerically, and solve semi-supervised seriation problems. So you know in these gene sequencing experiments, for example, that one read should be before another, or that two reads should be close to each other, etc. Well, every one of these linear constraints on the order just shows up as a linear constraint on the matrix capital pi. Okay? So every time you have additional structural information about the permutation you're looking for, you just add a linear constraint to the problem. Okay? So that's one very important fact. Just add linear constraints if you have information. And again, for gene sequencing, you do have a lot of structural information. The second thing I need to say is, okay, you solve the problem. Typically, you're still doing convex minimization over the set of doubly stochastic matrices. So most of the time, you get something inside. So you get a doubly stochastic matrix that's not a permutation. And the question is, how do you get a permutation out of a doubly stochastic matrix? So there are many things you can do. It's actually tractable to compute the nearest permutation matrix to the doubly stochastic matrix you're given. That's called the Hungarian algorithm. But that works, but not so well. And it seems that a very simple trick, which is to generate random monotonic sequences, apply pi, and recover the order, works quite well, actually pretty well, and it's very cheap. You just compute matrix vector products at each iteration. Okay? So it's, of course, exact if your matrix is a permutation matrix. Most of the time it's not. It's a doubly stochastic matrix, but you still get an ordering at the end by computing du, where u is this random monotonic vector again. Okay? And so basically what we do in practice, we solve the convex relaxation, and then we sample a lot of candidate solutions based on that very simple randomization procedure. Okay? So that's about it. So we get a large QP, but it's not so bad. So it's easy to solve with no numerical effort whatsoever, problems of size 100 or 200. You have this very nice pre-processing technique using the spectral algorithm. So it turns out that we can solve relatively large problems. Okay? So I'll spend the rest of the time I have showing numerical experiments to try to get you interested, and it's early in the morning, so graphics help. And so I'm going to measure performance of these solutions using several metrics. So remember here we're going to be comparing permutations, the true one and the resulting one. Well, how do you measure the distance between two permutations or the similarity between two permutations? There are many ways to do so. One is simply to compute the Pearson correlation between the two index sequences. Okay? That's called Spearman's rule. The second is to compute something called Kendall's tau. So we're going to take two pairs of points in each of the sequences, and we're going to say that they're concordant if one is smaller than the other, so both components are smaller or both components are larger. Okay? And the Kendall tau is simply the ratio of the number of concordant pairs minus the number of non-concordant pairs divided by, well, the number of pairs. Okay? And that's another measure. They don't behave. This one is a little bit more sensitive. One of the objective of our work was to get an objective to measure the quality of a seriation solution beyond what you get from the spectral solution. So one way to keep track of the performance of a method is simply to compute the two-sum objective, that combinatorial problem I just mentioned. Okay? And finally, if you know you're solving a seriation problem, you can simply count the number of R constraints that are violated, okay? So you know that on an R matrix, the coefficients should be decreasing as you move away from the diagonal, and you can basically count the number of times this condition is not satisfied at a certain number of indices, and that's another measure of performance, okay? So for historical reasons, I'm going to start with this example, which is relatively cheerful. You're trying to reorder chronologically graves, okay? So what you observe, and this is the original motivation for Kendall's work on seriation. So you have a matrix which represents, it's a 0-1 matrix. And it's a matrix that's 70 by 59, and it's artifacts versus graves. So they're trying to use the presence or absence of certain artifacts in graves to order them, okay? Meaning that all the graves from a certain period should have, roughly speaking, the same artifacts, okay? And so the idea here is that you want to solve the problem so that the matrix will be reordered and have continuous one, the C1p property over rows. Okay, so you permute the columns, which define the chronology, so that the presence or absence of an artifact is contiguous in the rows. Okay, and so on the left is Kendall's original solution, and that's 1971. So it's either an army of students or paper and pencil. But it's pretty impressive, right? It's already a permutation problem in dimension 59. So, and the data is quite noisy. And we'll see that this solution, which was done manually, does quite well. This is the solution you get using spectral ordering, and it looks good too. And this is the solution you get by semi-supervised seriation, and I'll say a few words on where the structural information comes from. There are interesting things to say about the numerical results. So here it's the 4 measures of performance I mentioned before. So Kendall-Tau, Spearman's rho, the two-sum objective, and the number of violated R constraints. For Kendall's solution, the spectral solution, the QP relaxation, and the QP relaxation with additional structural information. So where is the structural information coming from here? It's very simple. We compute a solution, and then we read from the solution some pairwise ordering constraints, and we add these constraints to the problem. So we generate information out of nothing, but it seems to help, which is kind of interesting. So in particular, if you add structural constraints from the original Kendall solution, you do a little bit better than Kendall, but Kendall beats all the other instances, okay? And so this is an interesting scenario where the semi-supervised solution does better than the original solution, even though you haven't added additional information. You just plug hard constraints coming from the first solution. So it's a bit bizarre. But with combinatorial optimization, everything is bizarre. Anyway, so that's the first example. Another example is Markov chains. So you observe random permutations from a Markov chain. So again, you lose the chronology. And so here it's a simple Gaussian Markov chain written in this way. And what you know is that the mutual information matrix decreases with the distance between I and j when the variables are ordered according to the true Markov chain. That's it's called the information provocation inequality or something like that. It has a name like that. It's in Cover and Thomas. And that means that the mutual information matrix in our case is a pre-R matrix, meaning that there's a permutation of it which recovers the correct chronology, which turns out to have this nice R property, okay? And so, well, we can do some simulations. So this is a very simple Markov chain, the true mutual information matrix. We obviously randomly permute the observations. And this is the solution you get from the spectral algorithm. And this is the solution you get from the QP relaxation. And with the QP, you can try many, many instances because there is a random element to it, and just keep the one with the best objective. So this is the best out of 100 experiments. And you see that it's the way it looks very similar to the true one. That's a kind of nice and intuitive example. We have absolutely no idea what this could apply to. So if you have a good application for this, I'm really interested because it looks cute. It's on Markov chain, so it should be fairly universal, but we don't know what to do with it. Okay. And finally, I should show you numerical information. So you can clearly see that everything breaks apart in the spectral method as soon as the noise is larger than the spectral gap, and that the effect of structural information is pretty strong. It starts to be pretty strong even if you don't have too much of it. Okay, so this is Kendall's toe between the true Markov chain ordering, the spectral solution, the QP, and the QP with some structural information. Okay? And what you see, obviously, is that when you have no noise, the theory tells you that the spectral solution is exact, and you see that Kendall's toe is 1. It's a correlation. And you see that the QP solution is not so good. Okay? Same thing here. As soon as you add structural information, in fact, a lot of it, it starts to get better, but it's a relaxation, so it's not exact. And if you keep, so what we do here is that we compute the mutual information matrix using very few samples, so we have a lot of noise, or a lot of samples, so we don't have too much noise. And we calibrate the number of samples so that we stay inside the perturbative regime, so the noise is smaller than the spectral gap, and then we remove samples so that at one point we leave the spectral regime. Okay? And so, when the noise is within the spectral gap, the spectral solution is still stable and works quite well. And as soon as you move out, the spectral solution completely collapses. Okay? That's nice. And you see also that this is monotonic in the number of pairwise information you get, observations you get. And so it seems that the semi-supervised version works. Okay, and to finish, I'll show results on DNA. And again, because you use the spectral solution as a pre-processing step, you can solve these things on very large, very large, it's your definition or mine, but it's a non-issue to solve this on large data sets. So, for example, here we have a shotgun gene sequencing read data set on chromosome 22, and we get 250,000 reads, and we get the spectral solution in 2 seconds. Okay, so without any effort, numerically speaking, and we use that as a starting point. And the idea here is that for genes, we're going to start by using the spectral solution. It's going to get some parts of the sequence right, and as soon as some parts of the sequence are right, you can collapse this part of the problem, and the problem shrinks. Okay, so you reorder using spectral. Some of the sequence is correctly assembled, you shrink it, and you're now left with a much smaller problem, and you repeat until your problem becomes small enough, and it actually takes 1 iteration, but it could take more, so that you can use the QP relaxation. And as soon as you use the QP relaxation, you can add structural information that you get and finish the problem. So this is what we do. And so how does it work? You don't know the correct order, of course, but you know when you got it right when you look at the overlap matrix. So that should be an R matrix, so it should have the R property. And so this is basically a plot of the overlap matrix corresponding to the spectral solution on this chromosome 22 data. And you see that some sections are perfectly assembled because, well, if you look at the corresponding overlap matrix, it has the R property. And then for other sections, there are issues coming from, for example, some parts of the sequence being repeated and so on. Okay? So this is a zoom on 2 regions because the matrix is 250K by 250K. And so this is what happens when you do spectral as a pre-processing step and then use the QP relaxation with some structural information to finish the job. Okay, the spectral solution, so this is a plot of index for the recovered points versus index in the true solution. So if it zigzags, you've got some points wrong, and if it's a line, then you're fine. You got the correct ordering. It's a very direct way of visualizing the solution. And so this is a spectral solution, so you can see that some large segments of the genome are correctly assembled. You can immediately shrink them, collapse the problem over these segments, so everything, the dimension shrinks significantly. And then for others, there is some ambiguity, okay? And so if you start from the spectral solution, shrink the problem, and try to reorder the segments using the QP with some structural information coming from the sequencing process, this is what you get, okay? And so I'm not at all an expert on genome shotgun gene sequencing assembly, but most of the algorithms used at this point for de novo sequencing are heavily combinatorial and local. People form these graphs, et cetera, and they build a solution piece by piece locally. And I haven't found a reference where they've tried the spectral solution to see how well it works. And so, well, it seems that it's kind of spectacular to see that this very naive procedure works so well. So we're going to try to run it on full genomes. There's no numerical limitation to do so. There's a bit more preprocessing, but that's it. The main computational bottleneck is computing the overlap matrix, the R matrix of similarity information, but that is naively parallel. So it's a non-issue, okay? And the spectral solution is almost instant, immediate, and the QP, well, typically you start it when the problem has dimension 100 or 200, so it's a non-issue. And it seems to work relatively well. So hopefully this will go somewhere. So just to conclude, we've shown the equivalence between the two-sum combinatorial problem and seriation for a certain type of matrix, matrices A, okay? We have a very simple QP relaxation for semi-supervised seriation, so seriation with some side information, and it seems to have relatively good performance on shotgun gene sequencing, okay? Open problems, so approximation bounds in the case where you only use the doubly stochastic constraint. I think it's fairly easy to generalize existing results when you add orthogonality constraint and relax it, but numerically this is quite challenging. And it would be very interesting to try to quantify the approximation quality of the simple doubly stochastic relaxation, okay? But it's not clear exactly how the randomization procedure we have now can be analyzed and so on. So if you have ideas, I'm really interested. Of course, we would like to solve the large-scale QP and exploit structure efficiently to get really large instances instead of the ones we do now. And also, it's not clear what the impact, you can choose many similarity measures, you can generalize the results to unimodal matrices with unimodal columns and rows instead of just binary. And so clearly, the similarity measures you use have an impact, and we don't know exactly how to pick them. Okay, that's it. Thank you very much.
Questions?
Yes. Okay.
There's an older result, I think in the 70s, that shows that you can solve a consecutive continuous ones problem in linear time.
Yes.
It's phrased up in a graphic.
Yeah. I've heard about that one, yes.
The other thing, though, is that so for the consecutive ones problem, there is this there's this log approximation algorithm for reordering to get the best under certain ones functions. I guess it's not obvious whether when you do this mapping, you have this works in the exact case, how it breaks when you now have noise. When you have noise in your system and you're using this convex relaxation instead, if you collude the relevant consecutive ones that you get, is there a cost function there that you could then try to optimize using approximation algorithms to get something useful?
I don't know, but typically you would want to play with, so for the shotgun gene sequencing experiments, you typically get errors in the reads and so on. So one way to make the problem more robust is to use different similarity measures than just overlap, okay? And then what you get is essentially unimodal matrices. So you have the same result, you use a different matrix product, but roughly speaking, the spirit is exactly the same. And that tends to be more robust. So that would help, I think, in a noisy case. And I agree that the other results you mentioned are probably faster to solve the C1P problem, but it's not clear what kind of behavior tolerance to noise they have. Yeah. And it's the same thing with all the classical techniques to solve the genome assembly problem. They're heavily combinatorial, and since you have noise, this is really tricky. Yes? The greedy? Greedy, basically. It would be greedy, right? Yeah, so for gene sequencing, you have... Oh, okay, so is there a reason why we ignore the simple greedy procedure where you take a candidate and then look for the nearest point in the cloud, okay, of other remaining points? Is that your question, roughly speaking? Okay, so the idea is that that's greedy, and it works if your sequence is noiseless and does not have repeats. And the key difficulty in genome assembly is that some sequences of the genome are repeated because we're very poorly designed. And so basically, if you do that, you can branch out to an assembly that's completely incorrect, and then you're stuck. Okay, so in the gene assembly, not only do you have noise because you make some mistakes in reading base pairs, you also have structured noise in the problem that's almost adversarial because of these segments of the genome that are repeated. And so you really need to look at a global objective to overcome this limitation and add structural constraints. Otherwise, the problem is unsolvable. Okay? So that's why greedy fails, I think. It's the structured noise.
Ben, do you want to set up maybe? It's already set up.
Yeah, it's in there.
I've got a very quick question.
Yes.
So you have this Frobenius penalty.
Yes.
Which is trying to push you more.
Yeah.
But at the end, you're not getting a permutation matrix, if I understood it correctly.
Yes.
You're sampling.
Yeah.
So does it hurt your computation time to make it sort of flatter versus you find that it does help even though you're randomizing?
We haven't checked. You mean, is it longer to solve when we concavify a little bit? Probably, but
But it does help even though you're randomizing.
It helps a lot the quality of the solution. So you're closer to a permutation matrix that's supposed to be good. It's a very heuristic statement, but that seems to work. But in terms of computing time, I don't know.
Thanks.
Thank you.